Okay, so let me begin by a quick review of the previous lecture. So in the previous lecture, we talked about simply connected groups. Simply connected Lie groups. The Lie group is simply connected if any loop on the group can be shrunk to one point. And we saw examples of simply connected groups. We also saw the example, say, I mean, SO2 is not a simply connected group, but it has what's called a simply connected cover. So I didn't specifically use this term. We will talk about this later in the course, but at least it's good to indicate that we have this homomorphism from the real line onto SO2, which we defined last time. And the real line is a simply connected Lie group. Any loop in the real line can be shrunk because it's a convex space. You could just shrink along the, with the convex combination. It's kind of intuitively clear that this is simply connected by the definition. And it has a homomorphism onto SO2 with a discrete kernel. In this case, we call R a covering of the group SO2. And it's a simply connected cover. Simon, you had a question? What do you mean connected under multiplication?
Yeah, R is a multiplicative.
No, R is with addition. R star is with multiplication. R star is a group with multiplication. R is a group with addition only. Well, actually, R is a matrix Lie group, but it has to be embedded in some way inside some GLNC. But we can choose the embedding, say, as matrices of the form 1T01. So this is a good question. So how is R a matrix Lie group? Well, it doesn't have to embed as diagonal matrices necessarily. So maybe I should write it here. We note that R is the set of matrices of the form 1T01 between R. Okay, so this is the way it is a matrix Lie group. Inside GL2R, or you could think about it as a subset of GL2C. Okay, and we also talked about this embedding. I'm sorry, the surjection from SU2 to SO3. Okay, so I left some of the details to complete to you. And I will still leave this. I will skip to a different topic. But if you have any questions about the argument, I'm happy to describe in the office hours or send me an email. I'll explain this. The book explains this argument and also postpones parts of it to exercises. It's really not a difficult argument. But the main point is that we have this homomorphism from SU2 onto SO3 with the kernel being plus minus 1, which is still a discrete subgroup. As a subset of SU2, it's discrete, closed, and there's no every single point is closed. Okay, well, maybe the complement of a point is closed also. So anyway, it has a discrete topology. And again, so here SU2 is a simply connected cover of SO3. Okay. So we've been talking about matrix Lie groups, but we want to push things to the more general setting. We want to stay away from these matrices for a while at least and talk about a general Lie group. So a general Lie group would be a group which has the structure of an open subset of Rn in some sense, okay? Or Cn in some sense. But how do we talk about open subset of Rn and Cn or more general spaces of this kind? There's like general machinery in mathematics called the theory of manifolds, which you don't want to talk too much about, but I just want to give some definitions to give you a flavor of this area. So first, we need to talk about spaces which at least locally look like Rn. And these spaces are called, well, at this level, topological manifolds. So here is a definition. A topological space is called, well, M is called a manifold. So I'll just call it a manifold, but it really means a topological manifold. I mean, we can talk about smooth manifolds and CP manifolds momentarily. We will talk about them momentarily, but for the moment, just take it as a manifold. So if it satisfies the following two properties. The first, which looks like a technical condition, but that's also important for some reasons, which, okay, I'll briefly explain, is that we want this space to be Hausdorff, which means any two points, distinct points, can be separated by disjoint open sets, and second countable. So what is second countable? It means it has a countable base of open sets. There's a countable family of open sets such that every open set can be described as a union of this, some subset of this family. Now, if you haven't seen the notion of second countable, don't worry, it doesn't play any role, any serious role anymore. Okay. And the second is that every point of the space has a neighborhood. So every, say, m, little m in capital M has an open neighborhood. Say U, which is homeomorphic to Rm, to Rn. So let's say for some n. I mean, if the space is connected, then you can see that the n will be constant overall. All these subsets should be homeomorphic to the same Rn. That's not a difficult argument at some level, okay? So you can assume it's always the same n, okay? So the idea is clear. So we want spaces which locally look like some Rn. I mean, you could say locally like Rn or some open subset of Rn, because if you take any open subset of Rn, it always like if you take any open subset, you can take any small ball, and the small ball of any radius is homeomorphic to Rn as well. So it doesn't make a difference if I say it's homeomorphic to a subset to an open subset of Rn. Okay, it will be the same definition. Okay. But what we do with manifolds is we usually want to take functions on them and differentiate functions. So really want some kind of way of differentiating things. So the topological structure is not enough for that, because composing a homeomorphism by differentiable function doesn't necessarily give a differentiable function. You might lose differentiability because you only have continuity, maybe not differentiability anymore. Okay. Therefore, we have to impose some differentiable structure on the manifold. And this differentiable structure can be at different levels. You want to ask maybe the functional just differentiable, or differentiable with continuous derivatives, which we usually call C1, or n times differentiable, or like p times differentiable with continuous derivatives. This will be the class CP, or maybe infinitely many times differentiable with continuous derivatives of this. So depending on the choice of level of differentiability that you want, you have a corresponding atlas. Okay, so this is the next definition. So let X be a Hausdorff space, a Hausdorff topological space. Which can be a manifold, but just Hausdorff is enough for the moment. An atlas of class CP for P bigger than or equal to 0, say. On X is a collection of open sets with some maps. So it's a collection of pairs, say ui phi I in some index set. With the following property. The first is that we want the UIs to form an open cover of the space. So each UI is open, and X is a union of the UIs. Okay. And the second is that we want these maps to be homeomorphisms to open subsets of Rn. So each phi I is a homeomorphism like phi I from ui to some vi, where vi is an open subset of Rn for some n. And the third condition is that we want the transitions between the phi i's form CP maps. So for all I and j and I, the transition to this map that goes first via inverse. So the picture would be the following. So we have this ui and we have this uj, and this is the map phi I, and this is this image vi inside some Rn, and this is this image vj. Well, these two images don't overlap, of course. They're really in different spaces. Okay, so we would like the map that's obtained by composing on wherever it's defined. So we should take this open set and we should look at the domain, which is phi I of this intersection, ui intersect uj, and it goes to phi j of ui intersect uj. Okay? It should be uj. Sorry, I'll correct it momentarily. Sorry. So we want the transition map, which is now a map from some subset of Rn to another subset of Rn. Maybe different n's or maybe the same n, but as I said, for connectedness reasons, they will be the same. You can actually show that they are the same. So we want this map to be, so the transition map, so the map, this map, the transition map is a CP isomorphism. So what does it mean? It means it's homeomorphism, which it should be because it's obtained by composition of homeomorphism and of class CP. So class CP means p-fold derivatives of this map, p-fold partial derivatives of this map are continuous. So it's continuous. Derivatives. So what is the advantage of having this atlas? The atlas is given on a topological space, but allows you now to differentiate maps there. Because if you wanted to take, say, up to a p-fold derivative of a map on this space X, say this manifold X, what you could do, so this is, say, X, which is a manifold, with maybe CP atlas. And now you have a map defined on some open set here. Let's say some open set, which is contained in some UI, doesn't matter. You have some map F with values, say, in R. So what you can do is you can do the transition by I to this VI. And now you can differentiate this map because this is now a map from an open subset of some Rn. R. So this differentiation is calculus. You can do this now. And now you can then pre-compose with the phi I to get a map, the derivative at the level of ui. But now you might say, okay, what if I use another set uj in the atlas? What function do I get as a derivative? Well, this assumption that the transitions are indeed also of the same differentiability class says that what this derivative that you get is well defined, and you get the same derivative. Okay. This is just calculus now. Okay. Basically, this assumption guarantees that you can do calculus. All right. So now, okay, so maybe some remark. The topological structure gives you a C0 atlas. So a C0 atlas is just a topological manifold structure. So no differentiability is required, right? So any manifold, the way we defined it, a priori comes with a C0 structure, okay? Now let me give you an example of some C1 structure. In fact, this is in C infinity structure, but doesn't matter. So example, maybe I should call it a C infinity structure. There is C infinity atlas. On S1. So what is S1? It's just a unit circle sitting inside, say, C in R2, okay? And now what we can do is we can take these two open sets by removing the north and the south pole. So this is like a 1, and this is -1. If you think about them, okay, so in my picture, actually, it's horizontal. So maybe I should just do the horizontal picture here too. So let's see if I can actually get a perfect circle. There's a circle. This is 1, and this is -1. So I take the sets U plus, which is like S1 minus number 1. That's homeomorphic. This is like by removing 1 point from this, you get an open interval. It's homeomorphic to an open interval, any open interval. And by removing -1, you also get an open interval. Or maybe I should say that this is homeomorphic to R anyway, because an open interval is also homeomorphic to R. And now I want to define an atlas. So I take these maps phi plus that goes from so maybe I should have chosen the interval 0 to pi, but anyway, I have made my choice already. So I take this map that goes from this into S1. So phi of t is phi plus t is e to the it. So clearly, this map traverses, the image of this map traverses the circle. It excludes 1 because e to the 2 pi I would have been 1, or e to the 0 would have been 1, but it's not included. And now what about the other one, this open set? I can choose a slightly different interval, but the same kind of map. So phi minus goes from, and this time from minus pi into S1. Phi minus t is e to the it. Okay, so e to the pi or e to the minus pi would have been -1, but that's not included. Okay, and now you can see that the transition map, phi plus, phi minus inverse, or phi minus, phi plus inverse, they are technically identity maps on some open subset of the real line. Okay, and so the identity map is really infinitely many times differentiable. So these two, they describe a C infinity structure, a C infinity atlas on the circle. Okay. So now you might say, why do we go through all of this? I mean, maybe we could have just thought about this as a subset of R2. We could have just induced something. Well, this is to think about spaces without embedding. So this issue that just arose, like, well, how is R a matrix Lie group? Well, we want to avoid these issues. We want to somehow give some intrinsic meaning to a Lie group. Okay, so we don't have to worry about embedding all the time. But that also leads to some challenges. So in particular, some very interesting and exotic examples, which was part of classical manifold theory, maybe from the 70s and 80s. This is really a classical subject right now, but it's still very interesting to know. So you might wonder, so, okay, so we got some C infinity structure here, but okay, maybe there's a canonical one, and this is really, we're doing some like extra work to define something which is always there. But that's not always the case. In fact, Milner showed rather so-called Milnor, constructed some different C infinity spheres at dimension 7. So basically different and non-equivalent, atlases. C infinity atlases. And S7 using octonions and sort of things. Okay. So even a sphere doesn't have a canonical C infinity structure. So you can have different ways of differentiating things. You have an embedding of S7 into R8, and that allows you to differentiate things by just inducing some smooth structure to the submanifolds by taking some orthonormal bundle or whatever, or some orthogonal bundle. So there is a way to, get one natural structure on S7, but there are many others, as Milnor showed. Okay, there are many others ways of differentiating things. Pardon? I'm not an expert in this area. I think maybe for S7 it is, but I think there are many open questions. But this is like a differential geometry. I forget. I've read about these things many years ago, but I don't remember. You have to look at some, standard references on differential geometry to get correct answers. Anyway, so as we see, things can be tricky when we talk about atlases, but we don't really want to do too much with atlases. For us, a more concrete sort of treatment is better, and we try to stay away from some like technicalities of atlas, right? But anyway, our definition of a Lie group in general will be based on this notion. So what is the definition? So just to make sure that we have the correct definition for the theory that we're developing, here it is. So a Lie group is a smooth, and a smooth means C infinity manifold. And when I say C infinity manifold, it means a manifold with a C infinity atlas. Okay. Which is also a group and the operations of multiplication Okay, so now you might say, okay, so now you defined R, SL2R, and so on, and now you want to stay away from matrix Lie groups, so then you should tell me what smooth structure you want to take here. Well, there are results that guarantee that on Lie groups, the smooth structure is unique. So we don't have to worry about that. But again, those results are really not easy to prove. So they're not going to be in the scope of this course. So for Lie groups, luckily, the smooth structure, the smooth atlas is unique. Okay, so we will not prove it. Okay, so let me look at the chat to see what's going on here. There seems to be a few things in the chat. If I could. Okay, no, there is nothing important in the chat. Okay. Okay, so for Lie groups, things are fine, and therefore we can somehow forget about atlases technically. Okay. Yes.
The smooth atlases are unique. What relation? Just technically, probably.
Okay, so we say two atlases are equivalent if the identity map gives you know, or rather, okay, so maybe, okay, so I mean, you can say that, okay, so you have these charts for one atlas, and for the other atlas, you have these charts. So you say they're equivalent if the transitions between them also have the same differentiability. They're in the same differentiability class. So in other words, you want, so phi I inverse O phi prime J's to be smooth. So this is an atlas on M, and this is another atlas on M, and we say they're equivalent if these transitions, I mean, if this is, for example, a CP atlas and this is a CP atlas, we say they're equivalent if these maps are all CP. So the notions of differentiability are the same. Okay. Well, just like what the condition that we impose on the atlas itself. Why do we impose this condition? Because we want different charts to give the same meaning of differentiability. We don't want the function to be differentiable with one chart and not with the other. Now, two atlases are the same if differentiability for charts of one or the other are really the same notions. That's what this condition is supposed to mean. Okay. Yeah.
Same level of smoothness.
Pardon?
They're at the same level of smoothness.
That is right. That's the same. If you want a CP manifold, two CP manifolds are equivalent if these compositions of charts between the two are CP maps. Okay. Okay, so now we can again kind of come back to our matrix world. After we have justified that we don't have to be in the matrix world, we can come back to the matrix world because it's convenient. And so the next thing we want to do is we want to talk about exponentials. But this time we want to exponentiate matrices. So given an n by n matrix, square matrix, with complex entries, say, we set e to the x to be the matrix that's obtained by this series. The same series that defines the exponential function. But of course, we have to justify that it makes sense. We have to justify that we have a convergent series. So to do so, we need to use, again, convergence in some Rn, but this time this will be Rn squared, basically, or Cn squared, okay? And then we need some norm, and the good norm for this picture would be the Hilbert-Schmidt norm on matrices. So given an n by n matrix, we define its Hilbert-Schmidt norm or simply norm X, because we will only be talking about this Hilbert-Schmidt norm for a while at least. So we define it to be the sum of absolute values of entries squared to the power 1/2, which is the same thing as a trace of x star x, or rather xx star to the power 1/2, or the square root. Now, here are some facts about this norm. The first is that this is actually a norm, which means the norm of a sum of two matrices is less than or equal to the sum of the norms. And this follows from the property of the usual Euclidean norm on Cn, okay? So this is the standard. And of course, norm of Cx equals absolute value of C norm X for a complex number C and X in n by n matrix. But more importantly, yeah. Oh, I have a question there. Oh, okay, sorry. Okay, so the question, does this X map coincide with the X map in the Riemannian geometry? Yeah, that's right. So you can actually show that it is in principle the same. Yeah, this is the reason why the exponential map is used. But here we have a I mean, we have a much more concrete picture. Over there, you have to use a metric and so on. Yes, but if you just, yeah, with some canonical choices, it will reduce to this thing. Yes, you're right. So this exponential map is a special case of the other exponential map, if you go through the definition there. So now, more importantly, the property of this norm is this multiplicative property. So norm of xy is less than or equal to norm x, norm y. And this is really a consequence of the Cauchy-Schwarz inequality. And that's because, so maybe I just write the proof here. So norm xy, it's really, so if you represent x by its columns, and y by its columns, so this is equal to, well, first you have to take the sum of the squares of the entries of the whole matrix xy, but you could do this with each column of the matrix xy. But the columns of xy are x times y1 up to x times yn. So this is now the usual Euclidean norm of xyi squared. And now we can expand with respect to the rows. So you actually get a double sum where you have xi. Okay, maybe I should have chosen these to be the rows. Okay, so yeah. So these guys are the rows of x, and these guys are the columns of y. So we get this. And now, well, here are the usual Cauchy-Schwarz for two vectors. Says that this product, this like the norm of this product, is at most, well, this is really an absolute value because this is just one number, right? This is just a 1 by 1 matrix, and it's less than or equal to the norms of the vectors x and y squared. So this is less than or equal to sigma xi squared, sigma yi squared. Maybe I just write it below. So it's less than or equal to sigma . So I basically use the Cauchy-Schwarz for each of the entries. So I have xi yj less than or equal to xi yj. Oops. And then I just sum over these guys to get to the last thing. I just then factor the sum in the most obvious way. And the last thing is just norm x squared, norm y squared. Okay, so here I missed the square, sorry. All right, so this is the proof. And now using this norm and this multiplicative property of the norm, we can prove that this series for exponential actually converges. Okay, so that's not very elementary. So here's a proposition. So the series converges for all n by n matrices. And the proof is just one line. The proof is that the norm of the sum, well, I mean, up to, well, so, okay, how do you prove a series converges? This is really, you should think about it as like a series of, with vector entries. So this is really like the entries give you vectors in CN2. So you have to show that it converges entry-wise. And for that, you basically need to show the tail of the series is going to 0. Okay, so if you take some tail part, something like I or well, n starting from some n to some m, with n and m very large. So this means n is very large. And you take the sum. So this is by the properties of the norm, it's at most norm x to the n over n factorial, or n from n up to m. But what is this? This converges to 0 because this is the tail for the series, for the power series, e to the z, for z equals norm x. So this is now elementary analysis. It's power series. This is like absolutely convergent series. So this tail should converge to 0 as n goes to infinity. Okay, and therefore, you have a convergent series up there. Now, here are some elementary properties of this exponential, this matrix exponential. So how many of you here in Ottawa are familiar with matrix exponentialized properties? How many of you have seen it, say, in ODE or somewhere? Yeah? Pardon?
I know.
Okay, from ODE. Anyone else here?
Right.
Okay, and you're undergrad, right? Okay, anyone else here? Third year linear algebra. People online, where have you seen this matrix exponential if you have? Anybody wants to say something? Nobody wants to say anything? All right, so, well, I'm sure that some of you have seen this. So here are some properties. So let x and y be n by n matrices. So first thing is actually that the exponential of the 0 matrix is just 1. That's just because of the series. You can see it directly. The second is that if you take the exponential and you do the star, the bar transpose, it is just exponential of the bar transpose. So bar transpose commutes with exponential, also transpose. But that's again a consequence of looking at the series. Okay. The third is that e to the x is always invertible with inverse e to the minus x. Okay. Number 4 is that e to the yeah, number 4 is maybe I just want to modify this slightly. So number 4 is that if x and y commute, then e to the x plus y equals e to the x, e to the y. And number 5 is that if you take some element of GLNC and conjugate x by that element, then the exponential of the conjugate is the conjugate of the exponential. So basically, all of these properties are totally obvious except for this one. Okay, all of them basically follow from looking at the series. So all follow directly from the series, from the definition. Except 4, and 4 is just like a convergence argument. So what you need to show is that the two sides, when you expand the series, their differences goes to 0. So let's write the two sides. So what are the two sides? So we just write sum, say I from 1. So for 4, maybe I just briefly explain how argument for 4 goes. So let's look at this summation. So this is the sum of the first m terms for e to the x. So this is approximately e to the x. And take the sum of the first m terms for e to the y. And now, what about the sum of the first m terms here? So this is approximately x plus y to the I over I factorial for I from 1 to m. But now you can expand, and you expand them, you get this binomial coefficient. I choose k, x to the k, y to the I minus k over I factorial. But then the I factorials cancel. So this is a summation over I and k. So what you get basically is a summation of the form x to the I, y to the j, I factorial, j factorial, with I plus j is at most m. Okay, because this binomial coefficient factors as like expands as I factorial over k factorial and like I minus k factorial. Okay, maybe I should just write it. And then the I factorials in the numerator and denominator cancel. You get xk over k factorial xy to the I minus k over I minus k factorial, which you can write like this. And if you load the exponents, so remember that here I actually has a range. So I is between, so maybe I should say k and I have a range. So here I lies between m and 0, but k is also less than or equal to I. So this is really the range. So when you rearrange terms, you get that. So I could now put the approximation of e to the x plus y here. Okay. Oops, I factorial, j factorial, I should have here. Okay. And I need to show that this difference goes to 0. But when you expand, now they have finitely many terms and you can expand. And what is left is the sum of terms where xi, where I plus j is bigger than m. Okay. So you basically end up with the norm sigma xi yj with I plus j bigger than or equal to m. Well, maybe strictly bigger than that, so maybe I should just put plus 1 over I factorial j factorial. There's a condition that I and j should be between 0 and m, right? So here we do have that condition because of the other condition coming from here. So I and j. Well, I mean, okay, maybe that's not a necessary condition. Of course, it follows from I plus j. But what I'd like to say is that, well, there is, of course, the condition that's I plus j is at most 2m. But we can just, so what we can do is we can first push the absolute value inside. And this will make the equality a less than or equal to. And then we can just remove we can remove this condition and consider all the terms. Okay. But now what we get here is the tail for this series, e to the norm x plus norm y. If you write the the terms of the series, you see you get because of this condition, you get the tail for this series, so it goes to 0 because this is like exponential of some real number. There's no matrices anymore here, okay? So it goes to 0. All right, so that's really the gist of the argument. But this is like classical analysis, and we don't want to emphasize too much on this. Okay, are there any questions? If people online, they want me to explain further, I'm happy to do so. Otherwise, this is just like an elementary analysis argument. Here, people do want me to explain further. Everybody understands? Okay, so that's just like, okay. All right, so now, using the matrix exponential, we can also consider curves on a obtained from exponentials. And these curves you've also seen in ODEs. All right, so how do you form this curve? This is the next proposition. So let X be an n by n matrix. Then we have this mapped that goes from R to, well, we can say MNC, but in fact, the image is in GLNC. And it's defined by gamma x equals e to the tx. Gamma t equals e to the tx. So then this map, well, is a map between two real vector spaces. You can talk about differentiability just like calculus, right? You don't need any manifold theory. And the claim is that this map is a smooth, it's infinitely many times differentiable, and in fact, its derivative at t equal to 0 is just x. Okay, this should be familiar to you from OD. I'm sure most of you have done this. Okay. People online, do you have any questions about this? The argument is really simple. So let me just briefly explain. So we have a convergent. So we have a convergent series. So, or maybe okay, more generally, maybe if we have a convergent series, so for any convergent series, okay, maybe I shouldn't do this in a general setting. Maybe I just should say that if you want to differentiate this, so you want to differentiate t to the n, like x to the n over n factorial t to the n. And you can differentiate term by term because the series is absolutely convergent. But then the derivative of each term is just n t to the n minus 1 x to the n over n factorial. So the first term for n equal to 0 it disappears, so you don't have to worry about it. So you end up with t to the n minus 1 over n minus 1 factorial because the n's cancel. And you have x to the n here, which is just x times t to the n minus 1, x to the n, maybe I just write below. Which is x e to the tx. So that's for arbitrary t, and in particular at t equal to 0, you get x. Maybe I should have given this in a more general setting. So maybe I should say this derivative at t is just x e to the tx, which is just x gamma x, e gamma t. Okay. Okay, so now we learned about this exponential, but of course, one thing that also shows up as a problem in ODE or in like applied applications is how to compute this exponential, because using the series is not easy. Okay, so here's an actual question: how to compute e to the x from x. So do you have a suggestion? Anybody here or online? Do you have a suggestion? First people here in this room. You have a suggestion?
Diagonalize it, then using the like the statement from the proposition.
That's right, exactly. So if you could diagonalize it, you could do this. And if you couldn't diagonalize it, then what do you do? So from this statement, so here's, what's your name? Justin. So Justin suggested correctly that if the matrix X is diagonalizable, we can use this condition to use a like first form a conjugate that's diagonal. The exponential of a diagonal matrix is a diagonal matrix with the exponential of the diagonal entries. So e to the diagonal entries show up on the diagonal. And now we conjugate back, so we get the e to the x. But what if the matrix is not diagonalizable? What can we do? Anybody online? Do you have any suggestion? Let me see if anybody online has a suggestion. Yeah, Simon, you have a suggestion, and that's actually very good. So we can use the Jordan form. So what is the idea of Jordan form? So what does the Jordan form mean? So Jordan form means that we can write X as a sum of a diagonal matrix and a nilpotent matrix. The Jordan blocks can be decomposed as diagonal plus nilpotent, and the diagonal part is just scalar multiple of identity. It commutes with the nilpotent part. So any matrix in the Jordan form can be written as a sum of diagonalizable and nilpotent. Such that they commute. And now what you should do is to compute e to the x. This is e to the d plus n. But what we saw is that if two matrices commute, we can write this as e to the d to the n. And now this is just the diagonal of, this is easy. And e to the n is just also like a finite sum. So if d is d1 to the n, then e to the d is e to the d1 up to e to the dn. All right, and the other one, like for the nilpotent part, is the finite sum. Okay, let me see how much time we have. Okay. I think we're okay with time. So any questions about this? I could do an example if you're interested. Anybody online or here would be interested in doing an explicit example of this exponential, or is it clear how we do this? Anybody here interested at all in anything?
I'd like to see an example.
Okay, Brandon, you want okay, that's good. Okay, so at least I can show an example. So let's take this matrix. Say, so here's an example. So x equals A, B, 0, A. So if B is non-zero, then X is not diagonalizable. But we can write X as A0, 0A plus B times this nilpotent matrix. This is AI plus BN. So I put an extra 1, sorry. Okay. And clearly the two commute. Identity commutes with everything. So here I didn't even need to diagonalize. If this was not the diagonal matrix, I would have diagonalized this by some conjugation, and then I would have another extra step. But here I didn't even need to do that. So e to the x now is going to be e to the ai plus bn, which is e to the ai, e to the bn, which is for e to the ai, I get e to the a, 0, 0, e to the a. And for e to the bn, well, I have to, so what is e to the bn? So this is 1 plus bn plus b squared n squared over 2 factorial plus 1 and so forth. But starting from here even, I get 0 because n squared is 0. Because n is a nilpotent matrix and of order 2. You can easily check. So you end up with the matrix 1 plus bn. So this is like e to the bn. So you get this matrix 1, b, 0, 1. Yeah. 1, b, 0, 1. And now you just have to multiply. So you multiply, you get e to the a, e to the ab, and e to the a. So that's how you do this calculation. Any questions? Okay, so we talked about the exponential of a matrix. What's the next thing we should talk about? If we have exponential, what do we want next to that? More natural than that? The logarithm. So when you have exponential, you should normally also have a logarithm. So let's see what we should do for defining a matrix logarithm. So the matrix logarithm is again defined by some series and using the following lemma. So here's the lemma. So the power series, or rather the function log z, defined by the series, which is -1 to the m plus 1 over m, z minus 1 to the m starting from 1 to infinity, is defined, i.e. it's convergent. And I will use this term, and I don't know how many of you are familiar with this, but I'll just want to use it. And I just want to kind of assume that you know what this means. Analytic in the set of complex numbers which are within one radius of number 1. Note that this is a power series expansion around 1. It's not around 0. So this radius of expansion should be computed around 1, not 0. Okay? And furthermore, e to the log z equals z for such z. So e to the any number makes sense. It's just that exponential series, which is always convergent for any complex number. Okay? The log, however, has some condition on the convergence. What the claim is that e to the log z, whenever the series for log z converges, which means z belongs to the set, e to the log z will be z. Okay? Should I assume this or should I prove this? Okay. How many of you are at home with this and you find that it's okay? But how many of you feel that you should give an argument? Pardon? Okay, we can prove it. Okay. Anyone online wants me to prove it? We have at least one vote in favor. That's enough. So how do you prove such a statement? Okay, so I mean, this is, you'd say, okay, this is trivial analysis, but anyway, we need some kind of proof, right? So how do you prove such things? If you don't want me to prove it, then you should at least have an outline. For those who didn't want me to prove it, can you provide an outline? How do you prove this statement? So first of all, the series should converge. Why does it converge? This is easy. Why? You guys should be able to do this. This is calculus. I mean, you can use any test, root test or ratio test, any test. Any test in calculus, you could see because the absolute value is less than 1 here, then you can see that by the root test, take the mth root here as m goes to infinity, this will actually converge to something less than 1. It converges to absolute value of z minus 1. Okay, so this is easy. Okay, but you guys should know this. You guys should be able to like. Okay, but then it's good to review this stuff because this is like foundational math. You always use these things, and it's not good if you make mistakes when you come up with such things. Okay, so therefore you should know what's going on, right? If you can do these things without making mistakes, then you don't need to write proofs of these things. But if you can't, then I think it's good to practice. All right, so okay, so we just know it's convergence, but now I use the word analytic, and analytic, so I will use this in passing somehow. Analytic means that this defines a complex function which is differentiable in the complex sense. How many of you know, how many of you have had a course in complex analysis? Okay, several of you, okay? So you know about complex differentiability. People online, how many of you, maybe you put in the chat if you have had a course in complex analysis? Okay, at least a couple, all right? So you're kind of familiar with this concept of differentiability. And we have a convergent, we have an absolutely convergent series. Would be great. We have an absolutely convergent series over complex numbers. The terms are polynomials, like it's anyways like a power series. So it converges to something analytic. Okay. Now, I wanted to show that this actually gives me the logarithm. How do I show this gives me the logarithm? What trick do we use? Why is it really log? Why should it be? Yeah. How can we show we have the log? Well, one way to do this is you could say, okay, I want to show, okay, so it doesn't look like the logarithm in any natural way, in any easy way, but what we could do is we could say, okay, maybe we can take the derivative and see its derivative is the same as the derivative of log, because log is kind of a black box, but the derivative of log is, pardon, 1 over t. So maybe we can also see the derivative of this guy is 1 over t in the right sense, okay? So this is the next step. So for t between 0 and 1, we can differentiate because we have a series which is analytic, so we can still differentiate. That's also another issue, whether we can or we cannot differentiate. But we could do d dt of log 1 minus t. And well, when we look at the terms, when we differentiate each term, the negative sign goes away because you get a negative 1 to the power m. You basically just are left with one negative sign, and then the denominator m goes away, so you get 1 plus t squared, basically, which is 1 over t minus 1, which is the right derivative, basically, because I have a 1 minus t here. If I change t to 1 minus t, I get the right derivative, okay? Oh, sorry, I have a minus sign. Sorry, I missed the minus sign. I guess I get oh, I think it was okay. Okay. But now if two functions have the same derivative, are they the same? Almost. Modulo constant. And we can check the constant. We can also check that log of 1 defined above is 0 by the series, because when you plug in 1 here, you get 0 in all the terms of the series. So really, we have the log. So this we've proved. So we proved that log t for t between 0 and 1 is the usual log. Okay. All right. So now we wanted to know if it's really the logarithm everywhere. Okay, on the whole domain. So how do we do that? Well, here you have to use analyticity. So here you know that okay, so in other words, what we wanted to show is this relation, right? Okay, so we could look at this relation first for z being like a number between 0 and 1. So we have e to the log t equals t for the above log, of course, for the above log t. And both sides are analytic functions. So we have e to the log z equals z for z in where both sides are analytic, which means for z and range for absolute value of z minus 1. So both sides, so this side is analytic everywhere. Okay, so this side is analytic everywhere, but this side is analytic wherever the exponent is analytic. Exponential function is everywhere analytic, but the log, as we saw, analytic only somewhere. Okay. All right. And so, I think I missed one last thing here, that I missed something in the statement. The last thing in the statement is that for any complex number u such that the absolute value of u is less than log 2, we have e to the u minus 1 has absolute value less than 1, and therefore we can talk about log of e to the u, and it happens to be u. Okay. So the proof of step 4 is the same. So you could basically just need to show this inequality, and then you could use the same trick as the step 3. So step 4, so we only show that e to the u minus 1 has absolutely less than 1, and the rest of the argument is the same as a step 3. We just use some analyticity. I mean, this relation that we want to prove, it is true for real t between in the interval 0, 1, not in the interval 0, 1, but for u with less than log 2 and real, and then it's true everywhere because both sides are analytic there. Okay, but what about this relation? How do we prove this? Can you prove this? So e to the u minus 1, what's its absolute value? It's the absolute value of u, because well, the power series for exponential is always valid. And this is less than or equal to absolute value of u plus absolute value of u squared over 2, blah, blah, which is e to the absolute value of u minus 1. But the exponential function is increasing. So exponential of e to the absolute value of u is at most e to the log 2 because of our assumption, right? And in fact, inequality is strict. So you get 2 minus 1, which is 1. Okay. So it's important to know what conditions we have. So I stated this lemma for a purpose. There is some condition here, okay? You might say, okay, it's like some numerical thing, and okay, we don't care about such things in theory. But it's easy to make mistakes. So if, for example, we take x, so here's this a simple but important example. So if we take, say, x equals like 2 pi I, 2 pi I. So then e to the x is 1, and therefore, so we could have used the same thing. So we could just say log e to the x. The question is it x or not? But this is really 1, and it is, I'm sorry, this is log 1. So e to x is, so e to the x minus, okay, I didn't write something here. Okay, that's why I got confused. So e to the x minus 1 is just e to the 2 pi I minus 1, which is 0. So it meets the condition of convergence if you wanted to talk about log e to the x, right? But when you plug that in the series, you get 0, which is not x. Okay? So you have to be careful not to make mistakes. And this is like, right? So you have to make sure you take the right branch of logarithm. Okay? Even an accomplished mathematician can make such mistakes. So it's important to be careful, right? We have maybe technically, okay, we have in theory 6 minutes, but in principle, maybe we have 1 minute left. But at least I can state the following theorem, or maybe the following definition, which will be our starting point for the next lecture. Oops. Something went wrong here. So my OneNote froze for some reason. Oops. Okay, so now what we want to do is now we want to use this definition of logarithm and the same power series for matrices. Okay. So here's the definition for next time. For any n by n matrix, say with complex entries, we define log A by the same series but where? For which A? Well, we want to give the definition as general as possible. So whenever the series converges. So one case, if A minus I, the Hilbert-Schmidt norm is less than 1, then log A is defined. Another example is when A minus I is nilpotent. It doesn't have any norm condition anymore. Because when you take A minus I nilpotent, the series will become a finite sum. So it's still valid. Okay. Okay, so maybe we stop here, and next time we'll just explore properties of matrix exponential, and we move forward towards what is called the Proter product formula. So that's really a key formula in basically theory, but also in perturbation theory, in applied in applied math, I would say. Okay. Are there any questions? Pardon? What does this question mean, being closed on the, so first you have to, like, what is the, yeah, what's the domain of this log map? But you can see that even for GLNC, this map is not always defined, because here the series might not converge for norm of A minus I large.
So it's not even necessarily one.
It will not map invertible matrices to invertible. It will map invertible matrices to arbitrary matrices close to zero. The exponential map maps a neighborhood of the zero to a neighborhood of identity. And around there, you can have the log map defined, because I minus A should be have norm less than 1. So like the image will be close to identity, and it will bring it back to near zero. So that's the idea. So neighborhoods of zero and neighborhoods of identity are now in correspondence. But now the question is how far you can go. And some classes of Lie groups, like nilpotent Lie groups, the exponential map gives a diffeomorphism between the whole Lie algebra and the whole group. So yes, but that's just because those groups are pretty close to the nilpotent setting, nilpotent matrix setting, so to speak. But there's a question in the assignment related to what is the image of the exponential map. Okay, see you everyone on Monday.